Welcome to lecture 44. In this lecture, I will be talking about gravitational waves from Einstein's theory of general relativity. To get started, recall that in lecture 20 and 21, we discussed the weak field limit in the regime of gravity. So in those lectures, we used the weak field limit to a particular purpose, namely we needed to fix the constant on the right-hand side of Einstein equations. So we used the weak field limit there to express the Einstein equations as a limit of the Newton equations, so that we could use Newton's constant to fix the constant on the right-hand side. In this lecture now, we want to use a different purpose for the weak field limit, which is that we want to look for a wave equation for the metric field g mu and discuss basically waves in gravity or gravitational waves. And one of the objectives of this lecture will be to calculate the speed of propagation of gravitational waves. To get started, recall that the Einstein equations are given here in equation 44.1. We are dropping the cosmological constant and we are dropping the energy momentum tensor term. So basically are looking for Einstein equations in pure vacuum. Recall that the weak field limit is defined as the metric field, which can depend on the coordinates, as some backward metric, which is Minkowski space, which here is denoted as eta mu nu, and it's just the diagonal matrix with plus or minus 1 in a diagonal. And then the non-trivial correction is denoted as h, where the weak field limit supposes that h is always in magnitude much smaller than 1, so that it is a correction on Minkowski space. If this is the case, we can plug the weak field limit ansatz, so this ansatz here, into the Einstein equations. The resulting expression is lengthy, but we could use, for instance, symbolic manipulation software to express the Einstein equations in terms of the field fluctuation h. And the equation we get here is written down in equation 44.3. Now note that there are sort of second order derivatives on h here. So this is a second order equation, but it still looks kind of messy and complicated. Okay, so linearizing the nonlinear Einstein equations gives a second order partial differential equation for the metric field fluctuation. This field fluctuation, therefore, this field equation, therefore, is a wave equation for the metric field. But because it still looks very complicated, we want to sort of employ our ability to express this in more suitable terms. In particular, we have not used the fact that GR is invariant under diffeomorphisms, so coordinate changes, and we can use this freedom to simplify the expression for the wave equation. To take a step back, what this is all about, let's take a different theory, which most of you will be well aware of, which is Maxwell's theory of classical electromagnetism. The equations of motions in Maxwell equations in vacuum are simply that the derivative or the divergence of the Maxwell field strength tensor F mu is equal to 0. And the field strength tensor itself is expressed in terms of the gauge potential A. So the Maxwell equations in vacuum then take the form 0 is box A nu minus d mu d nu A. So these are Maxwell equations in vacuum. The box here, as usual, denotes the square of the fourth derivative. And we can use Maxwell equations as a sort of proxy of what we want to do with the Einstein field equations. So recall that the field strength tensor F mu, which I sort of have written down here for classical electrodynamics, is invariant under gauge transformations. So if I change my vector field A mu to a different vector field tilde A, which is given as the original field plus the gradient of any function lambda, then if you plug this into F mu, you notice that because of this minus sign, this gradient term here drops out, and F mu is unchanged with respect to the original field here. So that means that different gauge fields A mu give the same field strength tensor. The field strength tensor denotes in electrodynamics the electric and the magnetic field. So they are different. The electric and the magnetic field are independent of the particular gauge choice of that we choose for the vector field A. So this is sort of invariance with respect to gauge transformation. We can use this freedom to fix the gauge to make the equations of motion simpler, since we know that changing the gauge does not influence any of, or does not change any of the physical quantities, such as the electric and magnetic field. A particular gauge choice is, for instance, d mu a mu is 0. This is one particular choice for that fixes the gauge freedom here. And if you sort of use this particular gauge, then the gauge fixed Maxwell equations, these equations here, because d mu a mu is assumed to be 0, become simpler. They become just box a mu is 0. So that's kind of the spirit of what we can do in electromagnetism, and we just want to copy this over now for gravity. So for gravity, of course, we don't have gauge invariance, but we have something that's very, very similar, which is invariance under general coordinate transformations. So we can use this freedom to sort of choose coordinates to fix the gauge such that the linearized Einstein equations, the wave equation that was given in 4D4.3 becomes simpler. In electromagnetism, one particular gauge choice that we could use was the divergence of the vector field be equal to something. And again, we sort of used it as a motivation for trying to fix the gauge in gravity. So for gravity, we'll try something similar. We'll try the divergence of the metric field is equal to something. And since we are still in the weak field limit, the metric field is a constant plus h. The constant vanishes under derivation. So this condition here would sort of become d mu h mu is something, and the something we choose is, for instance, this is a particular gauge choice, where h here is just a trace of the field fluctuation given here. So in this particular gauge, it turns out that the Einstein equations, the linearized Einstein equations, simplify considerably. And if you look back at equation 44.3, this expression here was much more complicated. Using this particular gauge choice, we just have that the Einstein tensor here becomes -1/2 times box of this particular combination h mu -1/2 h eta mu. Of course, we can still sort of simplify this further by just changing notation. We can sort of denote this particular combination as a fluctuation h bar or bar h. In this case, if you sort of choose this notation, the Einstein equation vacuum in the linearized regime become very simple. They become just box h bar is equal to 0. So once we sort of have gauge fixed, we find that the gravitational field obeys a wave equation. The wave equation looks very similar to the one in electromagnetism, and we basically have a gravitational wave for gravity. So now that we have a solution, or that we have an equation for the gravitational field fluctuation, we can use this to actually calculate the propagation of the speed with which gravitational waves move in empty space. Just a reminder, the way to calculate the propagation speed is via calculating the group velocity for wave packets of gravitational waves. The group velocity, in turn, is defined through the knowledge of the dispersion relation, omega as a function of k. And the group velocity then is given as derivative of the frequency with respect to the wave number k. Now, that just says that if we have the dispersion relation, we can calculate the group velocity, but we haven't calculated the dispersion relation yet. We can do this fairly easily by essentially going to Fourier space. So we transform the metric field fluctuation h bar to Fourier space. So the Fourier space transformed fluctuation is then called h tilde, and we have a 4 wave vector spanning together the frequency and the wave number in space. So plugging this into the wave equation, we find that the wave equation has a solution. The solution sort of relates the frequency and the wave number of the gravitational wave. And this is nothing else but the dispersion relation that we were looking for. So using this dispersion relation, it says that omega is equal to the absolute value of k for a gravitational wave in vacuum. And that in turn can be used to calculate the group velocity for the gravitational wave in vacuum. It's just the derivative of the omega by dk, which is just 1. So just as a reminder, we are in natural units. So a group velocity of 1 means that the speed of propagation for a gravitational wave is exactly equal to the speed of light in vacuum. A similar calculation shows or gives the phase velocity, which is defined as omega over k. That also comes out to be equal to 1 for a gravitational wave in vacuum. So then basically both the group velocity and the phase velocity are equal to the speed of light, which just shows that gravitational waves propagate exactly equal to photons in the empty universe. We are almost done, but there's more to the story. In particular, you should recall that picking a single gauge condition usually does not fix the gauge completely because there is some residual gauge freedom left. And we want to employ this residual gauge freedom to say more about the particular sort of structure of the gravitational wave. In particular, we want to discuss the physical polarizations of the gravitation. It is again useful to recall how this works for Maxwell equations because it is much more sort of familiar to most of us. So in classical electrodynamics, we said there's a gauge choice, and the gauge choice can be used to fix some of the parts of the vector field. I want to sort of change the gauge choice from the example that I had before. In particular, I want to now use a different gauge choice, namely temporal axial gauge, which says that I want to set the zero component of the vector field to 0. So if I do this, then I have fixed the gauge. But if I look at Maxwell equations, d mu f nu is 0, then if I look at the zero component of these Maxwell equations, these become d mu or d0 di ai 0. Which kind of still has the feel that there is a residual sort of gauge freedom left. In particular, it says that the time derivative of diai is 0, which just means that diai is a constant in time. So that's a residual sort of constant that we can fix. And indeed, one particular choice for this constant would be 0, so that in addition to the original gauge choice a0 is 0, we have a second gauge condition that just says that diai is 0. So then we have basically two gauge choices or two gauge fixing conditions. And that means that the original 4 component of the vector field in 4 dimensions get reduced by 2 because we have 1 and 2 gauge conditions, so that there are only 2 physical degrees of freedom left, which is what you all know about. There are only 2 physical polarizations for the electromagnetic field. In gravity, it works exactly the same way. So we have chosen a particular gauge condition before, which was d mu h bar is 0. By analogy with electromagnetism, we can impose a second condition on the magnetic fluctuation, and we sort of do that very much like in electromagnetism. We choose the 0 component of the magnetic fluctuation to be vanishing, and then that means that only the spatial components of h bar are actually physical. So in terms of the original fluctuation h mu, which is the difference between the full metric field and the Minkowski space, we can rewrite these 2 gauge conditions for h bar by using equation, I think it was 44.9, to relate the field h for these sort of 2 conditions. And we find that the divergence of h mu, the original h mu in here, is given as 1/2 times the gradient of the trace of the fluctuation. And the second condition is that the 0 components of the metric field fluctuation are given as, again, the trace times the Minkowski space tensor. So now that we have these 2 conditions, we can sort of explore in more detail. We can, for instance, write this gauge condition here in components. So if you look at the zero component here, you find that H00 now downstairs is -1/2 times the trace H. If I write down the trace H in components, it's just the sum in Minkowski space over all the individual components of H, so minus H00 plus all the spatial ones. And because there's an H00 both on the left and the right-hand side, I can bring this H00 on the left-hand side, leaving me 1/2 H00 to the left is minus the sum of all the spatial components on the right, which just gives that H00 is minus the spatial trace of the components. Now, this thing is one condition on H. The second condition, for instance, follows from here. I can solve this for H naught naught, which means that the full trace, this combination here, must be equal to -2 times H00. So I've written one of the gauge conditions in components. So now we can look at the second gauge condition, which was that the divergence of the metric field fulfills this condition. And then for the zero component of this in Fourier space, we find that basically the divergence of this becomes omega H naught naught is 1/2 times omega H. Note that we have used the fact that these gauge conditions up here can be used to rewrite some of the spatial components. And then what one finds is that since H here, according to this equation, is -2 H naught naught, we find that the right-hand side is equal to minus omega H0. So then we have omega H0 is equal to minus H0. And that means that the only solution to this two conditions is that the zero component of the metric field fluctuation is exactly vanishing. So now that we have this condition, we look back up here, we find that the trace H is also 0. And then we find that this condition here simplifies to K mu H tilde mu nu is equal to 0. We can further sort of simplify this by considering a particular direction of propagation for the gravitational wave. Let's pick the Z or X3 direction. In this case, the wave vector here only points in the X3 direction, so this only has one component where it's non-vanishing. And okay, this is just writing down the wave vector now fully explicitly. There's a frequency part here and a single direction where the wave vector is non-vanishing. Then this gauge condition here just implies that the third component of the, or anything that has a 3 in the direction of the metric field fluctuation is also vanishing, because we have that all the components in the time direction are vanishing. So long story short, we find that the trace condition H is 0 now has only two components left, which is just H11 and H22. So this in turn then fixes another one of these components, namely, for instance, H22 is minus H11. And then we have basically fulfilled all these sort of requirements for gauge conditions, so that if we summarize what we have done is we have fixed the gauge with a particular gauge choice, and we have looked at a gravitational wave traveling in the X3 direction. And if we do these two things together, we find that all the zero component of the metric field fluctuation vanish, as do all the components that have a spatial direction in the same direction as the gravitational wave. And in addition, we have that the diagonal components fulfill this condition here. If we still remember that we are dealing with a metric field fluctuation, the metric itself is symmetric in indices. That means that also the field fluctuation is symmetric in indices. And then we find that this condition just, for instance, means that H12 needs to be equal to H21. So that fixes another one of these components. So then after all these gauge fixing, we find that there are only two non-independent components of the metric field fluctuation, which you can take to be H11 and H12. If you want to write this down fully explicitly, H mu nu then is a tensor. It's a 4x4 matrix for a four-dimensional gravitational field. These conditions here mean that both the 0 and the 3, so best the first line and the third line, the first column, the third column, all have to be 0 because of these two conditions. These two conditions mean that the diagonals have to be such that the trace of this metric field fluctuation also vanishes. And the symmetry requirement says that H12 needs to be the same component or in the first off-diagonal entry here. Okay, so we find that just like in electromagnetism, a gravitational wave has only two physical degrees of freedom because there are only two physical or there are two independent degrees of freedom in our metric field fluctuation here. So the two physical polarization for the gravitational wave, even though h mu has many more original components as a tensor. So if you look at this tensor here, and even if you use that it's symmetric, you could have written down 10 independent components here, but the gauge or the Fermat-Wilson invariance restricts the number of degrees of freedom severely, and you basically start boil it down to only two independent polarizations. Now, how do these two polarizations look like if you basically have a gravitational wave moving through space? So if you imagine yourself having a sort of a circle of particles in front of you, then a gravitational wave can basically distort these sort of circle, and there are two physical polarization. There's what's called a cross mode that sort of will distort the circle in this particular fashion here. It looks like an X, so that's what's called cross mode. And there's a plus mode, that's the second physical polarization that will change the form of the circle in this like plus-like shape here. So to reiterate, Einstein equations give us gravitational wave solutions. There are only two physical polarization of this gravitational wave, and these gravitational wave solutions propagate at the speed of light.